Welcome to ERC Tipsnology. In this video, we will be learning the different circuit theorems and conversion. And we will start with part 1. This presentation will cover the DC voltage source, current source, source conversions, superposition theorem, and the other parts will be discussed later on. Let's start. The objectives of this presentation is to describe the characteristics of a DC voltage source, to describe the characteristics of a current source, to perform source conversions, and to apply the superposition theorem to circuit analysis. As an introduction, some circuits are not easy to do or to analyze using just the different laws in electronics or in electrical circuits, like Ohm's law and Kirchhoff's laws. We need to use other method to make it easier for us to understand the analysis of the circuits, and the theorems and conversions that we will discuss today will make the analysis easier for different types of or certain types of circuits. The methods do not replace, or it doesn't mean that we will never use Ohm's law or Kirchhoff's laws, but we will be using these methods together with the other laws in certain situations. Now, all electric circuits are using voltage sources or current sources. That's why it is important for us to understand how to work with these elements. And the superposition theorem will help you in dealing with circuits that have multiple sources. So first, let's start to learn about the DC voltage source. The DC voltage source is a principal type of energy source in electronic applications. It ideally provides a constant voltage to a load even when the load resistance changes. So the topics that we will discuss here are the following: the characteristics of a DC voltage source, practical voltage source, ideal voltage source, effect of loading on a practical voltage source. Now let's start with the unloaded ideal voltage source. As you can see here, we have a voltage source with the positive and negative polarities, and we also have the letter A and letter B to represent the part where we can connect our load. Now, right now, we don't have any load here. That's why it's called unloaded. Now, the familiar symbol that you see here is for the voltage source or the ideal DC voltage source. And the voltage across terminals A and B will not change, or it will become fixed even if you put any load resistance here on the letter A and letter B. And the ideal voltage source has an internal resistance of 0 ohm. Now, if we put a load resistors or a load resistor between A and B, like what you see here in the figure, all the voltage value from the voltage source will be taken by the load resistor RL. And ideally, the RL can be changed. You may change the value of RL except 0, and the voltage will still be the same. So this is what happens when we load the ideal voltage source with a load resistor. Now let's try to analyze the unloaded practical voltage source. So this time you will see that the word practical, it's no longer ideal, and because of that, the voltage source, as you can see here, has an RS or internal resistance here, RS. In reality, in real life, there is no voltage source which is perfect that does not have RS, or there's no ideal voltage source in real life. So, regulated power supplies are used, but it can only approach or become ideal when you operate it within a range of specified current. Now, all the voltage sources have some inherent internal resistance, as you can see here, as a result of their physical and or chemical makeup. Now, the RS here, or the internal source resistance, is connected in series with our voltage source or the ideal voltage source. So together, they are called practical voltage source, and the VS is the source voltage. Now, when you don't have any load here in the output voltage, with no load, the output voltage from A to B will be equal to Vs because there's no load. So the voltage here is equal to Vs. So the Rs does not affect as of now. And this voltage is just called open circuit voltage. Now let's analyze the loaded practical voltage source, and you will see here that we put in an RL between A and B this time. And all of the source voltage now of Vs will not go or will not be taken by RL because there is a series Rs over here. So some of the voltage that is supposed to go to RL will be taken by Rs because Rs and RL are in series. But remember that if the resistance is small, then the voltage drop that it will take will also be small. If Rs is very small compared with your RL, the voltage source will approach ideal or close to ideal because almost all of the source voltage, let's say 99% or higher, of the voltage source will go to RL. So it's like ideal, but not really ideal. It's only close to ideal voltage source. So very little voltage will be taken by the internal resistance Rs. Now, if you change the RL, let's say you change the RL, most or majority of the source voltage will still go to the output RL because it will have a much larger voltage because of its much larger R or resistance compared with Rs. And as a result, very little change will occur in the output voltage. Even if you change the RL, it will not really affect too much the value of the VL or the voltage on RL because your Rs is very small. The larger the RL is compared with your Rs, the less change there will be in the output voltage. Now, in example 1, we will show you the effect of changing the RL on the output voltage when the RL is much greater than Rs. So let's see the example number 1. What's the effect of loading on a practical voltage source? Let's say that we want to calculate the voltage output of the source in this figure with the following values of 100 ohms for RL, and let's say that we have 560 ohms also, and we will try to make it also as 1 kilo ohms. I mean, if we increase the value of RL from 100 to 560 to 1 kilo ohms, what would happen or what will happen? Let's see. Let's start with the RL equal to 100 ohms. Now, by using the voltage divider rule, where this is applicable to series circuit, we can use the R over R plus R multiplied to V. The R at the top will be RL, and the R's at the bottom will be the sum of Rs plus RL, and we will multiply it with the Vs, which is 100 volts, and we will get 90.9 volts. In other words, from 100 volts voltage source, it will be giving 90.9 volts to the RL. As you can see, this is a practical voltage source, and the RL does not get completely the 100 volts that is supposed to be given by Vs. What happened to the 0.1 volt? Of course, the 0.1 volt goes to the Rs. This is what we are saying. It's not a perfect or ideal voltage source, but it's almost ideal. But I'm sorry, but it's not 0.1, but it's 8 point or 9.1 volts. 9.1 volts were taken by Rs. That's big. 9 volts or 9.1 volts taken by Rs is big. And you will wonder why. Let's move on to the next one. If the RL is increased to 560 ohms, the answer will become 98.2. So you see here that the Rs is no longer taking 9 volts or 9.1 volts. If you look at it from 100 volts, the RL was taking 98.2. In other words, there's 1.8 volts missing. And where is that 1.8 volts? It goes to the Rs. But in comparison with the first RL, of 100 ohms, when we increase the RL to 560 ohms, from 90.9, it becomes 98.2, which is good because the amount of voltage taken by RS is now getting lower. From 9.1 volts, it becomes only 1.8 volts. Now, if we further increase the RL to 1 kilo ohms, then the V out using the same formula we will be getting 99 volts. And this time, we only lost 1 volt from RS. So to conclude this, we can say that the higher the RL, it would be better for the circuit because the RL will get higher voltage from VS if the RL is very much higher than the RS. But if the RL is lower or very low compared with RS, then the VS will never give majority. It will give majority, but it will have a higher value given to RS. Like here, we got only 9.9 in the output, but here we got 99. See, the difference is great. Here we only lost 1 volt, but here we lost 1.1 volts. Now, to move on to the next, you try to determine the voltage output of the same circuit, but this time, change the RS to 50 ohms and use 10 kilo ohms for our RL, and you find out what will happen. Now, to move on, we will say that the output voltage will decrease or become lower significantly, or there will be a great lowering of the output voltage if the load resistance, RL, is made smaller compared to the RS or compared with the internal source resistance. Now here, let's determine the V out for RL 10 ohms and RL 1 ohm in the same figure. So if you made the 10 ohms for the RL, we got 50 volts. And where's the figure? Let's see the figure. This is the figure. We have 100 volts. And this time we have only 10 ohms of RS. And the RL is also 10 ohms. If that happens, we will have 50 volts only. You see that? Imagine from 100 volts of the voltage source, it's only giving 50 volts to the RL. That's too much cutting of voltage. And why did that happen? Because our RL is only 10 ohms. And it's equal to the 10 ohms of RS. Now, if you made it much, much lower, like 1 ohm only, right? RL is only 1 ohm, which is very low compared with 10 ohms RS, then you will only get 9.09 volts from the voltage source of 100 volts. And that is unacceptable. Of course, 50 volts is not good already. Imagine I need 100 volts and I only take 9.09 volts here. That's not good because it means that 98.91 volt goes to the internal resistance, and that's not good. Therefore, our conclusion is really do not make the RL much lower than the RS. Instead, make the RL much greater than the RS. Now, you try also what will be the V out with no load resistor in figure 3. You see what will happen if the RL is equal to 0. What will happen? Now, let's continue to talk about the different kinds of source. That is the current source. This is another type of energy source, and this is used ideally to provide a constant current to a changing load. Now, the concept of the current source is very important in certain types of transistor circuits, which you will maybe study in your later courses. Now, the topics here that we will have are the characteristics of a current source, comparison of practical current source and ideal current source, just like what we did before with the practical voltage source and the ideal voltage source. Here, we will be talking about practical and ideal current source and what's the effect of loading on a practical current source. Now, let's see here the symbol for the ideal current source. You see here the circle with an arrow pointing upward, and we have here IS. So this symbol, without any internal resistance here, is the symbol for the ideal current source. And the arrow here tells you the direction of the current. Now, the ideal current source will give a constant or not changing value of current through the load between A and B, regardless of the value of the load. It means that even if you change the value of the load RL, you change its resistance, it will never be affected. The current will still be 100% taken from the IS. Now, this concept will be illustrated in the next figure, letter B, where a load resistor will be connected to the current source between A and B. And the ideal current source has infinitely large internal parallel resistance. Take note, parallel resistance. It's not in series. Later on, you will see that. See here, in the loaded current source, we loaded an RL between A and B. And what will happen? The load resistor connected here between A and B, what will be the effect of this? The ideal current source has infinitely large internal parallel resistance. Therefore, the transistor will act basically as current sources. So, transistors act basically as current sources. So, when you do the transistor topics later on, you will see that the transistor is a basic current source. So the knowledge of the current source is important, and you will find that the equivalent model of a transistor will really contain a current source. But we will be having that later on when we talk about transistors in other courses. So again, this is the ideal current source, and there's no internal resistance. Now, in the next figure, you will see that we placed an RS in parallel with the IS, and this is no longer an ideal current source because there's now an internal resistance. So this is called practical current source now with load. And although the ideal current source are used in most analysis work, no perfect or ideal device will be there, or ideal current source. Therefore, the most possible is that we will have a practical current source, just like what you see here. Now, what will happen here is that there's an internal resistance that appears in parallel within the current source of the practical current source, and the ideal current source without the parallel RS will now have a parallel RS. Now, if the internal RS is if the RS is very big or much larger than the RL, the practical source will approach ideal, or it's almost as good as ideal. It means that we need to keep the RS much lower compared with RL, or we can also say that RL must be much greater than the RS. So the part of IS here, the current that will come from the current source, will go through RS and RL. In other words, it will be divided between RS and RL. The IS will be divided between RS and RL. So, RL will never get 100% of the current source. The RS and RL will be like a current divider, meaning the current will be divided between them. Now, if RS is much larger or bigger than RL, then it would take most or majority of the current. And we don't want that to happen. As long as the RL remains much smaller than RS, the current through RL will stay almost constant, no matter how much RL changes. So let's repeat that part. Part of IS will go through RS and RL, and the RS and RL will share, or the current will be divided between the two of them. Now, if RS is much larger than RL, or very big compared with RL, most or majority of the current will be taken by RS, and there will be very less current that will go to RL, and very little will go through RS. So if RS is much larger than RL, most of the current will go to RL. So RL will have higher resistance, therefore it will have higher current, and very less current will go to RS. As long as the RL remains much smaller than RS, the current through RL will stay almost constant no matter how much RL changes. So if you make the RL much smaller than RS, the current that will go to RL will stay almost constant, or it will never change no matter how much RL changes. Now, if there is a constant current source, you can normally assume that the RS is much larger than RL, that RL can be neglected. So this simplifies the source to ideal, making our analysis easier. So if you don't understand that, it means that if we have a current source and it's giving a constant current, or we call it constant current source, that will only happen if the RS is so much larger than RL. Because if the RS is very, very big or so much larger than RS, it will take less or very less current, and most of the current will go to RL. Because the RL is very, very small compared with RS, it will take most of the current. Remember that the resistance is opposite the value of the current. The smaller resistance gets higher currents. Now, the next example, example 3, illustrates the effect of changes in RL on the load current when RL is much smaller than RS. Again, if RL is very, very small compared with RS, we told that the current that RL will take will be great or large. Small resistance, big current. Generally, we have a rule that the RL should be at least 10 times. RL must be 10 times smaller compared with RS. So 10 times smaller compared with RS, so that the source will do its job as a reasonable or a good current source. Now let's have an example. Let's calculate the load current IL with a value of 1 kilo ohms for our RL. What will happen? If the RL is only 1 kilo ohm, using the current divider rule, which is R over R plus R multiplied with IS, then what will we get is RS. So if you want to get the current IL, you have to take the opposite resistance, RS, divided by the sum of the two resistors, RS plus RL, multiply with the current source going into this junction, which is equal to 1 ampere of IS. And we got the answer of 990 milliamperes. If you think about it, 990 milliamperes is like 0.99 amperes. 0.99 ampere. And we are supposed to get 1 amperes or 1 ampere, but we only get 0.99. It means that we lost 0.01 ampere only. Correct? Now, if we change the value of RL to a higher resistance of 5.6 kilo ohms, and we calculate for the IL again, we will be getting only 947 milliamperes, which is 0.947 amperes. Now, 0.947 is less than 1 ampere by how much? That would be equal to, let's say, 0.163, correct? It will become 0.163 less compared with the 1 amperes or 1 ampere. Now, if you remember, the value we lost here is only 0.001. Actually, we only lost 0.001 ampere here, 0.001. Here, we lost 0.163. 0.163. Therefore, what happened here is that the 5.6 kilo ohms, from 990, it becomes lower to 947 milliampere. It means that the higher the resistance, the lower the current in the load. Now, if we make it much, much higher, 10 kilo ohms compared with 1 kilo ohm, we only get 909 milliamperes or 0.909 ampere. How much is 0.909 compared with 1 ampere? We lost how much? 0.091. Here, we lost 0.091. So here, 990 becomes lower, 947. It becomes much lower, 909 milliamperes. Therefore, if the RL is higher than the RS, then the IL that will go here will be lower. That's what we are saying here. Now, you try to calculate for the load current. let's try to calculate for the RL. What will be the RL? Just for an exercise for you, what will be the RL if using the same figure, the load current IL is equal to 750 milliamperes? So what will be the load current? What will be the value of RL if the load current is 750? That's what we are asking now here in the next. Now, what about source conversion? How will we change the voltage source into current source and current source into voltage source? In circuit analysis, it is sometimes useful to change between the two kinds of sources. In this part, we will be talking about converting the sources between voltage source to current source or vice versa. And we will be also understanding what is terminal equivalency. Now, if you want to convert a voltage source to a current source, the Vs will just be divided by the Rs. Again, we just divide the Vs by the Rs, and we will already know how much will be the Is over here. We divide Vs here divided by Rs. You will know the Is, and then you will just draw the practical current source here with the parallel resistance. Let's try it with an example later on. But the value of Rs will be the same between the value of Rs of the practical voltage source. So the value of the practical current source Rs will be equal. And the direction of the arrow here tells you where the current is going from or going to. So the equivalent current source is in parallel with Rs. So this current source is parallel with Rs. Now let's try it with understanding first the concept of terminal equivalency. Equivalency of two sources means that for any given load resistance connected to the two sources, the same load and load current will be given or produced by both sources. So as you can see here, the IL here by formula is equal to Vs divided by the total resistance of Rs plus RL, because this is series. So IL will be this formula. Now for the voltage source, the load current is this, right? Vs over Rs plus RL. Equivalency of two sources means that for any given load resistance connected to the two sources, the same load voltage and load current are produced. So as we have shown before, the value of the IL when you are using the voltage source or the practical voltage source is equal to Vs over Rs plus RL. Now, if we are using the source current or current source, what will happen is that the IL will also be Vs over Rs plus RL. And to show it to you, if we will use the current divider rule, we will say that Rs over Rs plus RL will be equal to Is. But Is is Vs over Rs, right? So we can cancel the Rs here and the Rs over here. The numerator has Rs and the denominator has Rs, and it would give us the same IL formula, which is Vs over Rs plus RL. We can say that if the two sources have the same values of IL, then we can say that there's a terminal equivalency. So as you can see here, the IL and of the voltage source here, practical voltage source, is equal to the IL of the practical current source. That's why there is a terminal equivalency between. Now let's see an example for convert the voltage source here. Let's make it current source. And how will we do that? We will just divide the Vs 100 volts divided by the Rs, which is 47 ohms, and we will get 2.13 amperes. And you will just draw the current source as 2.13 amperes in here with the parallel resistor. And that's it. We have changed the voltage source into becoming a current source. And both of these will be equal to each other in terms of giving the current to the load and even the voltage to the load. Now you try this problem, you determine the Is like this and the Rs of a current source here equivalent to a voltage source with Vs of 12 volts. The Vs is 12 volts and the Rs is 10 ohms. So what will be the Is and the Rs? So just do the same way that we did in example 4. Now, converting a current source still to a voltage source, let's do the opposite. We will change the current source into a voltage source. Remember that this is the current source and this is the voltage source. Again, the RS will remain the same. Okay, and the polarity of the voltage source is minus to plus in the direction of the current. This is from negative goes to the positive. That's why it's pointing upwards. And the equivalent voltage source is the voltage source that we will have in figure 11. Here we will see that the current source now will be changed into a voltage source. So it's like that. The only thing we will need to know is how much is the voltage source and how much is the RS. Of course, we already know that RS here and the RS here will also be the same. So let's try it. Let's see this one. We have 10 milliamperes current source with an RS of 1 kilo ohms. Then what would be the value of the voltage source and how will it look like? All we have to do is to multiply the IS with the RS and we will get the VS. So let's do it. Let's multiply the 10 milliamperes with the 1 kilo ohms and we will get the 10 volts. Now, in the figure 13, the equivalent circuit will be looking like this. You see, the 1 kilo ohms or the 1 kilo ohm for RS and the 1 kilo ohm for RS here is the same. And they are the same. And the VS is not the same. It's not 10 milliampere. It's now 10 volts. The question is, how did we get this? We just multiplied IS with RS. And there you go. This is the example of changing current source into a voltage source. Now, you try it by determining the VS and the RS of a voltage source equivalent to a current source. If we change the 10 milliamperes to 500 milliamperes, what will happen? And let's change the RS to 600 ohms. So you try it so that you will know what will happen. Now, let's move on with the first theorem that we will be talking about is the superposition theorem. The superposition theorem, some circuits are more than one voltage or more than one current source. It means that in some circuits, there are two voltage sources or two current sources. And most amplifier is like a device, electronic device, that makes the signal bigger or greater. Most or majority or more amplifiers operates with two voltage sources, like there will be an AC voltage source and there will also be a DC voltage source together. That's an example of a device that operates with two voltage sources. Now, some amplifiers will need both positive and negative DC voltage source for it to operate properly. You will know that more later on when you have a course in electronics, introduction to electronics. This one is more on the introduction to electrical circuits. Now, anyway, when multiple sources are used in a circuit, it means two sources, okay? Two sources or more, we can use the superposition theorem to analyze the circuit. So we will be talking about how can we apply the superposition theorem in our circuit analysis. And of course, we have to know what is the superposition theorem. And the most important, what are the steps in applying the superposition theorem? Now, the superposition theorem method is a way to know the currents in circuit with more than one source, meaning two or more sources or multiple sources. And how do we do that? By leaving one source at a time. In other words, we will cancel one source at a time and do some calculations. And then we will put them together later on. Now, we will also replace the other sources by their internal resistances. Now, recall that the ideal voltage source has zero internal resistance. And the ideal current source has infinite internal resistance. Don't forget that note. Now, all sources, we will think of it as ideal in order to simplify the coverage. It means that we will ignore the possibility of having RS within the voltage source or the current source parallel. RS will not be there. We will assume like that it's an ideal voltage source and ideal current source. Okay. Now, a general statement of the superposition theorem is like this. The current in any given branch of a multiple source circuit can be found by determining the currents in that particular branch produced by each source acting alone, with all other sources replaced by their internal resistances. The current total or the total current in the branch is the algebraic sum of the individual currents in that branch. It seems so hard to understand, but just to simplify it, if we would like to know the current of a resistor, for example, we cannot do it directly. what will happen is that we will determine first the current of that resistor, thinking that there's only one source. So if you have two or more sources, you will need to cancel the other source or sources and do your normal series parallel calculations. And after you finish that, it does not mean you have calculated the current of that resistor, because you will have to repeat the same way, but this time the source that you cancel before will now be used, and the source that you did not cancel now will be the one to be canceled or removed in the next procedure. And you will then calculate again the current using some series parallel theorems, and therefore you will have two currents. If you have two sources, you will have two currents for a particular resistor. And then there's a third step to put the current of the first source, or using the first source, or with respect to the first source, plus the current with respect to the second source. And when you have done that, then you will be able to get the current of that branch. Now let's try it. Okay, what are the steps? Step number 1, leave one source at a time. It means do not do two sources. We have to cancel one of the sources and change that source. If it is a voltage source, we will have to make it shorted. If it is a current source, then we have to cut the source. That's what will happen. If it is a current source, you cut the source. If it is a voltage source, you make it shorted, or you make the voltage source like a wire only. Now we determine the particular current for that. We can determine the current or the voltage that you want, just as if there were only one source in the circuit. Therefore, in superposition, if you're not good in using the KCL, KVL, Ohm's law, current divider rule, or the voltage divider rule before, when we have only one voltage source or one current source, then it would be very hard for you to do the superposition theorem. So you have to do some review or revision of the previous lessons about the calculating currents and voltages first before you do the superposition. Now after that, step number 3, we take the next source in the circuit, and we will repeat step number 1 and step number 2 to do this for each source. And then finally, we will find the actual current in a given branch by algebraically adding the currents due to its individual source. And once you find the current, you can determine the voltage using Ohm's law. Of course, for normal students or for those who are new, this will be very confusing. The approach in superposition will be shown in the next example, so that it will be better for us to understand these steps. So let's say we have this circuit. You will see that we have VS1 and we have VS2. The question now is, what is I2? Now we cannot just say that the I2 will be depending on VS1, because it also depends on VS2. So how will we do this? We will be using, for example, the superposition theorem by doing the VS2 first. Let's make it like a shorted wire, or we will cancel the VS2 by replacing it with a short line or short wire here, shorted wire, so that we don't have any more VS2, and the resistance here will be 0, right? Now after that, we can see that it looks like the regular series parallel circuit, where we can calculate the R total, right? R1 plus the parallel R2, R3, and we can also calculate the I total with respect to the source 1 as VS1 divided by the R total. And because of that, you will get the I total with respect to the S1. Take note that the voltage source is no longer there. So we only have one voltage source. And this would be the formula to get the I total. And again, we are trying to get the I2, right? But we need to calculate first the I total. And after that, we can use the current divider rule, where if you want to find the current on R2, we would get the opposite resistor, R3, divided by the total of the parallel resistor, R2 plus R3. I hope that's clear. The I2 is equal to R3 over R2 plus R3 multiplied with the current that will go in to the junction, which is either I1 or I total. Anyway, they have the same value. I1 is also equal to IT. So now you will get the value of I2, but again, this is with respect to source 1. Now, let's go back to the original circuit. This is the original circuit. This time, what we'll do is we will look on the VS1 and we will change it into a shorted wire. So the short here replaced the VS1. So this time, we will analyze the circuit like a series parallel circuit, but the R3 will be the one in series with the source, and the R1, R2 this time will be the parallel resistors. And with that in our mind, what will happen is like if we want to calculate the R total this time, R3 will be in series. So the formula will be R3 plus the parallel of R1 and R2, and that would give us the R total. Now, again, the parallel of R1, R2 will be R1 multiplied with R2 divided by R1 plus R2. And then we will get the I total, which is equal to Vs over R total. Vs2 divided by the R total with respect to source 2. So this will be our main idea here, that we replace the first source with the second source before with a shorted wire. Now we are changing the Vs1 with a shorted wire. This is the second step. And then we calculate both the R total and I total, right? Now after that, we will calculate the I total with respect to the source number 2 with the current divider rule. Remember that the current I2 will be equal to the opposite resistor, which is R1, divided by the sum of the two parallel resistors, R1 plus R2, and therefore multiplied with the current going in to that junction, which is the I3, which is also I total of VS2. So we will multiply the I total of VS2 with the R1 divided by R1 plus R2. And we will get another I2 with respect to the source 2. Now, finally, we have to think about the third step. We got the I2 with respect to S1, and we get I2 with respect to S2. And you will see that our analysis shows that the currents are going downward, both of them. So we will assume to add them, I2 S1 plus I2 S2. And maybe if we got the answer as negative here, then we will know that the direction will be opposite. But right now, in our calculation for IS2 with respect to S1, we got positive. If we get positive answer, then it's downward. But if we get negative answer, then the assumption that it's downward will be upward. Same thing will happen to the I2 with respect to S2. If the answer here is minus, then you have to change the direction of your I2 S2. Okay? Now, because let's say that both of them has a positive value, then we can assume that our direction going down are okay. So is okay. Then we will add the I2 S1, I2 S2, and we will finally get the I2. That's why the superposition is not as easy as you think it is, because it involves a lot of knowledge in the series parallel circuits. Now let's put some values here. Let's put 100 ohms for all, just to make it easier. And we have 10 volts on the left and 5 volts on the right. Again, what's the first step? Yes, we have to replace the voltage source 2 with a short wire or shorted wire. And we will analyze the circuit as a series parallel circuit. And we will calculate our total as R1 plus R2, R3 divided by R2 plus R3. But because this is 100 and this is also 100, remember in the parallel circuits, when the parallel resistors are equal, we can just divide them by each number. So if there are two resistors in parallel and both have the same, we divide by 2. That's why you will see here that it's equal to R3 divided by 2. Now, if we think about this, this will be 100 plus 100 divided by 2, we will get 50 ohms. And the total will be 150 ohms for the R total with respect to S1. Now, I total will just be by Ohm's law, Vs over RT, we will be getting 10 volts divided by 150, 67.7 milliamperes. That's for I total. Again, we want to calculate I2, but we cannot do that without knowing first the I total here. After that, we now know the IT. We can find I2 by using the current divider rule, which is R over R plus R multiplied with the current entering the junction. Now, the current entering the junction here is I1 or IT. I1 and IT are equal, so it's okay to say I1 it's also okay to say IT here. And the opposite resistor will be used if you want I2. Take the opposite resistor between the parallel R3 over R2 plus R3, and we will get a value of 33.3 milliamperes for our I2. But it does not mean that this is the final answer, because again, we have to consider shorting the source 1 now. This time, we replace source 1 with a shorted wire, and let's see what will happen. In the analysis, the voltage source 2 will be used as the source, and the I total now will go to I3 or R3. So I total with respect to source 2 is equal to the I3. And the parallel this time will be the R1 and the R2. So the formula will look like this. Again, the R2 and R1 has 100 ohms each. Therefore, we can just divide 100 by 2. And we add it with the R3, which is in series with VS2. You have to change your mindset. You have to think that the R1 before is series with VS1, but this time R3 is the one in series with the source. That's why it will be R3 plus the parallel R1 and R2. And we got 50 ohms. 100 plus 50 ohms. We got 150 ohms also, because I made all of them equal, but you have to consider the values perfectly. I mean, if this is 200 ohms, you have to not divide it by 200 divided by 2, because if this is 200 and this is 100, you cannot divide by 2. You have to use multiply over add. So you multiply 200, multiply with 100 over 200 plus 100. Anyway, let's continue. We have to calculate I total by Ohm's law, and we got the answer of 33.3 milliamperes after taking 5 volts Vs and the R total of 150. Now, we got the I total. We can get now the I2 using the current divider rule, which is R over R plus R multiply with the current that will go to this junction. Now, remember that the R3 is the series resistor here, and R1 and R2 are the parallel. So, the I2 will be the opposite resistor, which is R1. That's why here we put R1 over the sum of R1 plus R2 and multiply it with the I total coming from VS2. That's why you will see here the I total with respect to S2. It does not mean you will multiply, all right? The S2 here means subscript. That means the I total with respect to S2. So what will be the answer? If you substitute them, we will get 16.7 milliamperes. Positive. So it means the direction that we assume is correct. But remember, we have I2 with respect to S1, and we also have I2 with respect to S2. So we have two I2s, right? So how will we find the final answer if we have I2 with respect to S1 and we have I2 with respect to S2? You see this? I2 with respect to S2 and I2 with respect to S1. All you have to do is to add the two answers so that we will find the I2 with respect to the source total. So what will be the answer for I2? I2 S1, which is 33.3, plus I2 S2, which is 16.7. Again, let's go back. The answer for our I2 in the beginning is 33.3. And then after doing the next step, we got the answer for I2 as 16.7. Now we add the two, we got 50 milliamperes. That's it. That's how to do the superposition theorem. And I hope you understand our lesson about superposition theorem. And for now, we will stop here, and you can watch the other videos that will teach you in our YouTube channel how to do the mesh analysis, how to do the node analysis. And there's these two are the same. It's just a way to calculate for the current of a branch or voltage of a branch resistor. So we can use superposition, we can use the mesh analysis, and we can also use the node analysis. But we will still find out the same answers when we calculate using the same circuit. Anyway, this is the first theorem that you learned, the superposition theorem. So good luck in understanding the mesh analysis and the node analysis that we will be also showing in our YouTube channel. Please subscribe to our channel to support us, and have a nice day, everyone.